Right, here is some last minute revision, and it is last minute because this is the day before the P2 exam, and I'm doing this with no preparation, so I'm not setting a very good example. But P2, topic 1, we've got a few sections to look at: electrostatics and electric current. So I'll start at the start. As you have to do in many other subjects, first of all, you've got to talk about the atom. You've got to know that the protons and the neutrons are found in the center of the atom, the nucleus, and that electrons circulate in different energy shells around the nucleus. You need to know the position, you need to know the mass and the charge. So the protons and the neutrons have got a relative mass of just 1, and the electrons, by comparison, are 2,000 times less massive than the protons and the neutrons. They are much, much less massive, and they carry a negative charge. Now, in terms of electrostatics, we want to focus on the negative charge of the electrons and the positive charge of the protons, and the simple fact that these guys, the protons, are stuck inside the nucleus. They can't, in a solid, the nuclei of the atoms can't move past each other, but the electrons might be able to move away from an atom, or they might be able to move to another atom in another substance. So if we take two materials, let's just think of two insulating materials such as nylon and polythene. Now if you get, these are both kinds of sort of plastics, and it just so happens that they two different things happen to them. If you actually rub these things together physically get two of these rods and rub them together, what happens is that the atoms on the edges that are rubbed together physically have their electrons very agitated. And I know for a fact that in the case of polythene, it's got a tendency to lose electrons. So some of these electrons in polythene might not be tightly bonded, and it might lose some of these electrons. And I know that nylon has got a tendency to gain electrons. So what can happen is that some electrons can be transferred from polythene onto nylon. What happens in that case is that because this nylon has gained electrons, it gains negative charge. And because this polythene has lost electrons, it is left with a positive charge. Notice that the only things that move are negative charges, the electrons that move. If we take two of these negatively charged nylon rods and point them close to each other, they will repel each other. So like charges repel. However, if we hold the negative nylon next to another polythene rod, they will attract. So like charges will repel and unlike charges will attract. It's a little bit like magnets in that sense. So we need to look at shocks. What can happen is that let's for instance draw a cloud, and on a sort of hot day the hot air rises upwards and it moves through the clouds of water vapor, and what can happen is that can result in that movement of air the air must lose electrons, and the clouds can build up negative charge. So we had a cracking thunderstorm here in Church Stretton yesterday. Clouds building up negative charge. Thunder is caused by the expansion, rapid expansion and contraction of air when hot air and cold air meet. But in this case, when things get a bit more dramatic, the charge can build up on a cloud to the extent that, let's say we've got an old church here, and we know that air is an insulator. It can't carry charges very well. The particles are far apart, and the particles aren't metal. They're made of, all kinds of things, but generally non-metal molecules. And so air is an insulator, but the charge can build up to such an extent that the charge can be attracted to Earth. And Earth, we sometimes give Earth a symbol a bit like this. Earth contains an equal number of negative and positive charges, and then things that are grounded, things that are connected to Earth, also have an equal number of positive and negative charges. And what can happen is that these electrons build up to such an extent that they are attracted to the positive charges in the Earth, and they find the quickest way to get there. They will, blink of an eye, navigate their way down as a bolt of lightning, and that is called a discharge to Earth, a discharge of negative charge, electrostatic charge, and that can cause quite a lot of damage. The amount of energy transferred very quickly can be quite significant, and so that could kill you if you happen to be on the wrong end of a lightning strike. And don't stand next to trees either, because trees are made of wood. They don't have much water in them, but they are taller than you, most of them. But the tree might take the brunt, but then there might be a little branch sticking out, and the lightning will prefer to go down you into the Earth. So you don't go near trees. In fact, if you stand with 2 feet on the ground, the current driven around your body may stop your heart. So the best thing to do, this might save your life one day, stand on one leg in the middle of nowhere, in the middle of a flat field. Stand on one leg. You will look stupid, but you will survive. We now need to look at something called, well, let's say we've got a rubber balloon, and this balloon is not to scale, so it's not half the size of a church, but I'm going to introduce this balloon to a wall, and this wall is connected to Earth, so it's got an equal number of positive and negative charges. And let's say we've rubbed this balloon on our hair, our jumper from Primark, lovely cheap material, so it's gained lots of electrons. It's negatively charged. If we introduce this balloon to the wall, it's attracted to the positive charges in the wall, and these electrons are repelled from each other, so these electrons will run away. And what you end up with, imagine now the balloon is touching, well, we get the negative charges attracting to the positive charges here. However, over time, that attractive force will disappear as electrons disappear to the Earth, or they themselves go through the wall, and eventually it's left in the same position as it was before, with a fairly equal number of positive and negative charges, and the balloon will fall to the floor. So we can have an attractive force between unlike charges. When we charge an object up, it can then repel the like charges in it, and be attracted to the unlike charges if there's an imbalance of charge. So electrostatics can cause things to stick to each other. In the case of, now there are some good applications of electrostatics. Let's say we are spraying a bike, for instance, a bike frame. Then this is a bike frame, for instance. Well, what we might have is a can of spray, can of paint, and if we charge the bike frame with positive charges, we might have to connect it to a battery or something or whatever, then what we can do, we can spray paint, we can give the paint a negative charge, and the negatively charged paint will be attracted to the positively charged frame, so you won't waste much paint. Likewise, if this paint is negatively charged, it will spread out nice and evenly because they will repel each other. The droplets of paint will spread out, fan out, because they repel each other and they are attracted to the bike frame. So you get quite a nice finish on the bike that way. I can think of some cases where you might need an earthing strip. For instance, if you've been flying through the air in a plane and the plane has got very charged up, then it might land on the ground, but its rubber wheels won't let any excess charge. It's very charged up and it's on the ground, but it's still very charged up. If you suddenly connected a metal hose to it to refuel it or something, there might be a spark, a discharge, as the electrons zoom down the metal hose. So what we want to do is we want to connect that to Earth with a safe bonding strip so that the charge can flow down to Earth safely without having to spark. So a plane might have an earthing strip before it's refueled. Similarly, a church might have a little conducting strip, a strip of metal that runs down its length to allow any lightning to travel down it safely. So you could also walk around with some kitchen foil around your head like that, and you will be completely safe. Which is more stupid, standing on one leg or wearing an aluminium foil hat? Who's to know? Okay, that's electrostatics for now. Thank you.